C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The FLEX TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovib's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research, simplifying thermal conductivity.
All right, good day, folks. Thanks for joining for today's webinar session. We'll go ahead and get started here in about a minute or two. Few housekeeping items just for the folks on the line there. Today's session will be recorded, available for playback after the session is over. There will be a shareable link, so if you did have to drop off early but wanted to see the rest of the talk, you can certainly check that out later, or of course send it to any colleagues that you might think would find some relevancy in today's discussion. I'll also make note of the Q&A feature in the Zoom platform. Throughout the session, if you do have any questions related to anything presented, maybe something more related to the work that you're looking to do, please feel free to type those questions in. We will reserve some time at the end of the formal session to do a little bit of a Q&A. All right. And with that being said, though, about a minute past the hour, so we'll go ahead and get started here today. Like I said, welcome. Thank you for joining us here today. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. And today our topic is measuring thermal conductivity on a budget using the Thermal Conductivity Kit, or TCkit. So this will be the focus of today's chat. Before we get into it, just do a little bit of a general introduction. So for those that may be new to C-Therm, a little bit about us. We focus on the measurement of thermal conductivity, specifically through the development of transient-based measurements. Really, throughout the development, our goal is really to simplify this measurement. Again, doing this under the guise of the transient class of measurement technique. So, at a high level here, and if you saw the intro video there, our core product, flagship product there is called Trident. You can see Trident on screen here. So this won't be the focus of today's chat, but I will just mention Trident is a modular system. It offers various methods for thermal conductivity characterization, a little bit more of a premium grade instrument. Again, of course, having different testing capabilities, but it also does have the TPS, and the TPS is what is going to be the focus for us here today based on the TCkit. So I'll make some comparisons between the two instruments here, but of course, really, we're going to be diving more so into the TCkit. So what is the TCkit? What's included here? Well, like I said, it operates off the same TPS style sensor. So in the kit, of course, you have one sensor. It'll come with a standard reference material, software, and of course, a setup guide. Again, it is a little bit more of course, a condensed system, but still gives you access to some nice introductory testing capabilities for a variety of materials. And we'll go into some examples of those here today. I will mention specifically the TCkit. We have some nice quick shipping options. I believe there is a link just posted in the chat by my colleague Angad for the Shopify link. So this is something that you could essentially access through that website, through that portal there. Gives you a nice quick and easy way to get at the costing information, as well as access to purchasing this if this was of interest. So I do just really, I'd say briefly want to compare specifically the TPS capabilities on the TCkit versus Trident, because there are some notable differences here. I mean, you can see them here all on screen. The thermal conductivity range is a little bit more limited there. The sensor that comes with the TCkit has an upper temperature limit of 80 degrees Celsius. So you still do have access to some temperature testing, room temperature, some moderately elevated temperatures as well. But of course, it is limited to 80 C. And when we look at the utilities here, and I'll go into some additional detail on this a little bit later, but the bulk utility is what is, I'd say, the same in the sense between the TCkit and the Trident platform. So it gives you access, again, to like these bulk solid material characterization. What you would be lacking or missing out on the TCkit is things like anisotropic testing, slab, and thin films. And I'll go into some examples of what those are essentially, and the types of samples that would essentially require those options for testing. But that kind of gives you the high level rundown there. The other thing I do want to point out specifically is the standard. So the TPS method, so the transient plane source, sometimes referred to as a hot disk style sensor, notably carries and follows the ISO 22007-2. The sensor itself between the TCkit and the Trident is essentially identical. However, on the TCkit, you would not be strictly conforming to the ISO based on a requirement for, it has to do with the controller unit. So with the Trident, of course, there's this dedicated unit for the data acquisition and kind of communication between the sensor and the software. It's a little bit different on the TCkit, and for that reason, testing using the TCkit would not strictly conform to the ISO requirements, although I would say a lot of the testing process involved will still carry very similar steps in order to go about doing the testing and validating your measurements. But that's kind of I'd say kind of an overview of the differences there. If looking at the TPS options that we provide, or thermal conductivity in general, maybe if you're new to this topic, we do have a method selection guide. It's available as a free download, free resource. Goes into some detail about the different methods that are available, of course, in industry, but also the ones that we would offer here at C-Therm as well. So a nice little guide, definitely has some good information in there. Feel free to take a look if you wanted to kind of see what's going on with the different options available for testing. I will also just mention here, so as kind of said at the beginning, C-Therm, we focus on thermal conductivity. We are partnered with both Rigaku and Metrovib in North America for their for Rigaku's line of thermal analysis tools, so DSC, STA, TMA, as well as Metrovib, as I mentioned, for their DMA testing options. Also, Thermal Analysis Labs. This is C-Therm's contract testing division. If you're interested in getting some data, excuse me, but maybe not ready to bring instrumentation in-house, certainly happy to assist from a contract testing perspective as well. TAL would have all of the instruments that we have available at C-Therm, as well as other options that are available in industry. So in either scenario, if you're looking for some testing or equipment, feel free to take a look there. We'd be happy to assist in either capacity. And for these, webinars, we always try to pick a client testimonial just to, share with everyone what folks are saying about us. This one here is specific to the TCkit. So it reads, the TCkit is easy to operate. A new user would not face difficulty in using it. The kit can also provide test results within minutes. As a whole, the TCkit is a useful device to investigate the thermal behavior of solid materials. The equipment is a great addition to our research lab and will allow us to open a new area of research. So this was from Dr. Hossein. He's a professor at Ryerson University there. We do have a list of client testimonials available on our website. So if you wanted to check out what other folks were saying, definitely invite you to do so. All right, that was a quick introduction to what we're going to be doing here today. So let's go into the topic of the TCkit. So as I mentioned, the TCkit, it utilizes a TPS, or transient plane source sensor. So I wanted to really break down what is a TPS, again, for those that may be new to this. So you can see a picture of the sensor there on the right. I'd say there's like two things to really flag. From a design perspective, the sensor consists of an electrically conductive material. So it's etched out of a thin film. So this is really the, what's going to be, the electrical system, what's heating up, delivering that thermal input for the measurement. But that component is encapsulated or surrounded typically with a polyamide. There's different materials of construction for different sensors, but of course that's to provide protection to the sensor itself, electrically insulating the system and providing some mechanical stability. One thing with the TPS is it is a double-sided sensor. So when we go to talk about the test setup, what samples you need for the measurement, and kind of the, really how the test is run, one thing to keep in mind is that being a double-sided sensor, we're going to be using 2 samples. So essentially creating a stack around the sensor for the measurement. So maybe to speak to this a little bit, this is, at a high level, the principles of operation. So how you go about setting up a measurement, what's involved. So like I said, it's a double-sided sensor. So on the left there, here's my pointer here actually. Again, your sensor is between 2 materials for testing. These samples, so the piece, so call it sample A and sample B, these do need to be viewed as identical materials. In the ISO, there's some verbiage on, of course, the types of samples and the recommendations, but there is this underlying assumption of symmetry. So the sample that is on top should be the same as the one on the bottom. To an extreme example, you wouldn't want to put like a piece of metal on one side and a polymer on the other, and kind of try to do a mixed measurement in that sense. They do need to be 2 of the same material, of course, and also things like, generally you want to have very similar considerations on the surface. The overall top and bottom should be as closely matching as possible. Now, once you get your sample set up, the next thing to take a look at is running, from the software side. What do we need to take into account here? So there's a couple, I'd say, parameters that we're playing around with in the measurement, mainly the time and the power settings. So how long are we running the measurement for? What is the total input that we're delivering to the sensor? So how much is it going to heat up by? These are parameters that are set by the user for the measurement. There are certain guidelines in place for, if you're testing something more insulative or more conductive, you need to adjust those settings accordingly. But unlike if you've been on webinars previously with when we talk about, let's say, the MTPS, which is calibrated, it's more of a point and click type measurement. The TPS does carry a little bit more operator influence in order to get things set up and running. Now, once you've got everything squared away from the sample and your initial parameters that you're going to run, again, with any transient-based measurement, that comes to the similar idea in that we're monitoring the change in temperature that occurs during the measurement that you're performing. But this data, once it's been collected, there is this final step, and with the TPS, it essentially involves a verification process. So there's a series of checks that need to be met in order for your results to be considered valid. The guidelines and the guidance on what these checks are and how you go about, doing them. A lot of the guidance provided in the ISO on this. But as an example, there are certain calculations that are run. There's something, for example, the probing depth, which we'll talk to, I think, in a couple of slides. But it needs to be within a certain range. And how we do this is by adjusting actually the region of data that we're analyzing. So not only as the user will you be defining your test parameters, but you also need to define the region of data that we're analyzing. So all that said, with the TPS, there is influence from the operator. There's some oversight, of course, that is required there. But the process in going through these validation steps, it's a stepwise progression. It's quite logical in its flow. But this gives you a way to, of course, ensure that the results that you're getting from the measurement based on the settings that you've used are giving you good data. The example I like to give is, if you had a TPS measurement set up and you use some combination, you analyze a specific region, and then you would send those samples to me, and I was to test the exact same material, but I did something completely different here. Well, we could in fact get two different results. So we have to have a way of ensuring a correct way of determining which one is in fact the valid measurement, right? So that's, I'd say, kind of the long and short of the testing process that's involved there. Now, I mentioned at when we were comparing TCkit to Trident, one of the considerations is that the TCkit does not strictly conform to the ISO. And part of that is because instead of a fixed dedicated controller unit, the TCkit operates based off a source measure unit. Keithley is a fairly common one that you'll see there, but essentially the TPS has a 4-plug connection that will connect and interface directly with the SMU here. Part of the design that is incorporated here is related really to essentially to how the resistance measurement is taken during that test. This is kind of a little excerpt from the ISO, essentially kind of showing some different components that are required to meet from just the physical device standpoint itself. Whereas the TCkit, again, it works off this 4-prong, 4-lead resistance measurement. At the end of the day, they are measuring resistance in their own way, but again, strictly to conform to the ISO guideline requirements, it has to have a very specific electrical design in the controller unit, which the TCkit does not have. So although the steps that you will follow in the measurement, a lot of the guidelines on what samples are appropriate, how you go about testing them will be identical. There is some differences there just fundamentally based on how that connectivity is obtained there. So just wanted to make that clear for everyone as you're going through and potentially considering these types of options for your testing. Now, in terms of samples, wanted to quickly touch on this as well. So your sample size for TPS is dictated based on the sensor that is used. With the TCkit, it comes with a standard 13mm sensor size. There's the one size option provided. And the material for measurement will scale based on that 13mm criteria. So the diameter of the sample that you're measuring needs to be 2.5 times the diameter of the sensor. It's about 32.5 millimeters, with a thickness scaling 1:1. So again, about 13. So you can imagine you're dealing with kind of like a puck style sample. It doesn't need to be cylindrical in nature. You could have like a large, square cubic shape sample. That's irrelevant essentially, as long as the minimum diameter size is met and the thickness is met, you're going to be able to take a measurement there. But the requirement and why this is, and I mentioned it there, one of the checks is the probing depth check. So there's essentially it's a little calculation that is run based on the measurement that you're taking, and we need to be within a certain window. There's a minimum that we need to be above and a maximum that cannot be exceeded. And this is based on the sensor size that's used. So ultimately for the TCkit, it's a little bit easier. You only have to really remember one range, and it's based on the 13mm diameter sensor size. But again, the summary here and the takeaway is that we're dealing with bulk size materials for characterization purposes. Now, again, we're going to look at some examples with the TCkit specifically, but I do just want to mention what I call them the more advanced utilities that are available on Trident do give you, because of course there are certain materials that, although you may see, again, a lot of publications, a lot of data out there on, these types of samples tested with a TPS, inherently they may require specific modes of operation. So there's the slab, anisotropy, and thin films testing side of things. And And this would inherently require the use of TPS on something like the Trident platform, for example. But I just want to quickly run through what they are, just so you kind of have that information. So the slab utility, it's when you're dealing essentially with sheet slab style samples, extending in 2 dimensions from the length and widthness perspective, but with a limited thickness. There's a little bit of a setup difference than your traditional bulk mode. You can kind of see here there's some insulation placed on the top and bottom sample. Ultimately, what this is for thinner, higher K materials. So really designed for those above 10 watts per meter Kelvin, but with a thinner sample format. An example of this, we've showed this data before in previous webinars, but something like a pyrolytic graphite foil. This is something that we tested with the TPS slab utility, exhibiting some very high, almost 1800 watts per meter Kelvin in plane thermal conductivities. So again, if you were looking and primarily dealing with these types of materials, be more of a fit for the slab utility on Trident. For anisotropic materials, the TPS does have ability to measure orthotropic samples. So those that would have, let's say, an in-plane direction that is the same in kind of the radial sense, but with a different through-plane thermal conductivity. Again, this is a form of material that you could test with the TPS anisotropy option. Couple things to note: you do need to know the heat capacity and the density of the material. This is required as an input into the software for measurement. Carries the same sample size requirements as bulk, but again, important to note that if the materials are not isotropic, the results obtained can be an error if you treated them as such. Just kind of a quick data set kind of example here, but seeing differences between the in-plane and through-plane, especially for more novel samples. I mean, a lot of polymers, different additives, can introduce anisotropy, the way they're formed, the extrusion process, all of these things can play a role. But again, if you were dealing with something that would exhibit a level of anisotropy to the measurement, this would be something just to keep in mind in terms of technical fit. And the last one here is for thin films. So when we talk about thin films, really talk about like freestanding polymer-based films. These can be down into the micron range, like 10 microns thick. Again, there's a little bit of a different setup process that's involved here. It's essentially a successive layering procedure. It's a 3-point measurement that is typically done. I have a snapshot here of what a test would look like on Trident. Essentially here we're building out a film thickness versus temperature linear regression to determine the thermal conductivity of these films. But again, related to something being in that micron range thickness size, again, wouldn't it really be a technical fit to treat it as a bulk material? It would require a little bit more of a specialized setup approach for measurement. So, in summary here, if you're looking at bulk materials, bulk isotropic options, again, this is something that's, of course, available on Trident, but this would be really what the TCkit is geared towards. If you were instead looking to measure, samples exhibiting anisotropy, high conductivity sheet slab style samples, or, polymer thin films, this is where you may want to consider looking at more of the Trident grade instrument for those purposes. But that being said, of course, there are a variety of samples that would fall within the realm of the TCkit's wheelhouse, let's say. So I wanted to kind of take you through a few different samples, different formats, different materials that do lend itself quite well to testing TPS and specifically on the TCkit. First one being, again, bulk solid, ceramics, and metals. An example of this that we've seen different applications come up are things like, brake pads, for example. So brake pads are, of course, there to slow you down and slow those cars down. But the way they function is essentially, it's through friction, and we're getting a lot of heat buildup generated during that operation. So, anytime you hear the words heat buildup, of course, thermal conductivity can play a role there in terms of optimal material selection, ensuring that it's meeting the specific requirements for the application. And again, with brake pads, I wouldn't say I'm a connoisseur of any vehicles in that sense. I mean, I do know that there are different types of brakes, metal, ceramic, different composite type systems that are out there. I guess just depending on how much money you want to put into your braking system. But as an example of measuring something like this, so again, a bulk material. This is essentially actually just off the shelf brake pad that was purchased. Fits essentially the sample size requirements for the 13mm TPS. And we can do some testing here. So we looked, quite simply at a semi-metallic versus ceramic option. From a thermal conductivity perspective alone, we're noticing quite a difference between those two materials for the brake pad application here. Again, there's a lot of other factors that go into, performance for something like a brake pad, but just from a thermal perspective, and again, general material looking to characterize the performance, thermal conductivity of those different sample types, TPS, the TCkit would be a great option to be able to kind of enter into that type of investigation. Another really big, I'd say, application that we see for the TPS in general, are more porous materials. A lot of construction building applications involving like concrete, asphalt, cement. These are samples that are a really good fit for the TPS based on the setup that's required. So the TPS, like I mentioned, you need two pieces, but it goes in direct contact with the sensor. There is no need for any contact agent, sampled coatings, or treatment involved. For example, I made reference to the MTPS earlier. A lot of solids with MTPS do inherently require a contact agent. If you're testing something like a cement, oftentimes, something like DI water would just absorb into the material. So it's not really the best fit for this application. Inherently, the TPS really lends itself quite well to these materials. Also, due to the flexible nature of the sensor, it provides a very safe way to go about testing those more rigid, rougher samples. It's not to say that you can't damage the sensor, but it is something that, decreases the likelihood. And also, of course, if you needed a replacement sensor because there was a rip or a tear, they're generally more economical than some other sensor designs that may exist in industry. So here we can kind of just see some data sets on something like a concrete. One thing to note is, I was mentioning the samples need to be quite, similar, identical between the top and bottom side. If you were testing something that does have a certain level of, let's say, heterogeneity to it, it's not perfectly consistent. One of the things, and of course this is, taking something that, if you read the ISO, there's some verbiage in there about, homogeneous materials. Most methods will inherently, they're designed to handle that. But if you have something that is not perfectly meeting those requirements, it's not to say we can't test them. But one thing that might be, good to keep in mind is taking multiple measurements to get a general an understanding of, the consistency in that measurement. If you move the sensor around, like for example, at different locations, are you seeing big swings in the results? Or is it relatively consistent depending on the test location that's taken? But again, really from just a material perspective here, the porous nature, the hygroscopic sample types, TPS is a really nice fit to go in and do that type of thermal conductivity characterization. And the last one, and I'd say probably one of the bigger areas or use cases is polymers. So, generally speaking here, again, bulk isotropic materials, many polymers would fall into that category. Oftentimes groups, of course, taking a base material, filling it with some type of additive, or maybe comparing different, polymer bases in terms of the best fit for the application involved. But with the TPS, again, a great way to go about testing a sample that looks like this. These are like blocks of samples that were cut. And the data that we'll show here, we're comparing a neat nylon to one that had one that was filled with a conductive material, just again, to do some relative comparisons there. So we can see here that the composite polymer, the one that had that additive, was, of course, as you might expect, in demonstrating a higher thermal conductivity than that of just the base material itself. So in terms of use case, again, whether you're looking at different materials or even just different variants of a control sample, kind of seeing are we getting closer to that thermal conductivity value that we're aiming for? Are we going the wrong way? What's going on there? TPS is a really, again, great way to go about doing that testing. And for a sample like this, again, a great fit for something like the TCkit. So, ultimately here, the TCkit compared to the Trident, I think we've gone over the differences there, but it really offers a nice cost-effective solution for measuring thermal conductivity of these bulk solids. Areas where we've seen this employed, I mean, like the testimonial shared, like a lot of universities doing some introductory research. In a kind of an educational setting as well, like it's a very small footprint. So if you have like the SMU unit and this TCkit box, which you can hold in the palms of your hand, very easy to bring that into a classroom. Again, simple enough to set up, kind of demonstrate the fundamental idea behind a measurement. And also, again, just for some introductory research purposes, it's a really nice tool. If you were, however, like I said, though, looking to do more novel materials like the thin films, anisotropic samples, slabs, that's really where we'd be more so, guiding you towards something like the Trident system. But again, depending on the testing needs, the TCkit definitely offers some nice introductory capabilities there. So, this really kind of brings us about to the end of today's session. Just wanted to give you a nice quick rundown of the TCkit. Going into a little bit of a kind of conclusion here, kind of the little outro. I noticed there are quite a few questions posted in the Q&A. So as I said, once we get through these next few slides, we'll go through those for those who are interested in staying on the line. But if you've been on the webinars before, we put these on quite regularly. All of the webinars are available, for playback on our website. So definitely feel free to take a look through the repository. There's a lot of great content, some more general, high level, different method comparisons. Others are very specific to a unique application. So definitely feel to check that out. Also, our tech library, oftentimes we'll reference various publications or groups that have used the sensors, sometimes external data, other times internal, but all of that can be found on the website there. I will also mention some upcoming webinars that are currently booked in for the next, I guess this is going about mid-April there for a month and a half out. Towards the end of March 20th, we'll actually be having more of a DMA-focused webinar. We have a guest speaker, Dr. Vincent St. Ange, will be talking about very high-frequency measurements of viscoelastic properties, again, with a focus on the MetroVib DMA system. March 27th, I'll be back with you guys to do more of a C-Therm focused webinar. Again, more of a targeted one on thermal conductivity and AI hardware, different components, different cooling systems. We'll take a deep dive on what's going on in industry, different kind of examples of where what these materials are being used for, and some of the considerations specifically for this, of course, the revolution that is going on right now in the AI space. And then April 10th, we will be back. I'll be joined with a few of my colleagues to talk about material characterization for food packaging and cold chain storage. This one will be a thermal conductivity C-Therm focus webinar, but also with some nice data from the Rigaku system as well as the DMA from MetroVib. So it'll be really like a full material characterization suite example on that application space. I'll also mention some of the events that we'll be at physically. So if you are, you happen to be in the area, or these are conferences or events you were thinking of going to, love to have a chat with you kind of in person if you're around. So this one is currently happening. One of our colleagues, Brandon Brown, is in Munich, Germany for the thermal management for EVs and HEVs. Again, that's currently underway in Germany. Later on, beginning of March, we'll have some colleagues at PitCon. This is in Boston, March 1st to 5th. And then later on, I guess same time there in the middle, we'll also be at JEC World in Paris, France, exhibiting there as well. So if you happen to be in the area and you're planning to go, love to meet up and have a nice chat if that'd be of interest. I'll also mention, if you're just looking maybe for some just more information, whether it's on anything presented here today or in general, feel free to reach out. We'd love to, have a chance, maybe do a more one-on-one technical discussion, learn about your materials. We could give you more of I'd say a tailored presentation and kind of walk you through some measurements on some representative materials. I'm happy to schedule those. Also, just wanted some quote information, some budgetary costing. Again, definitely feel free to reach out. We're happy to provide all of that. Last couple slides here, I'll just mention, give us a follow on LinkedIn. This is where we post all of, really say, the latest and greatest content, upcoming events, different, writing pieces, webinars, all of this gets posted here first. So if you're not already doing so, give us a follow there. And at this point, this brings us to the official end here. So we're going to go into the Q&A session at this point. I will go ahead and really stop sharing my screen, and we'll end the formal recording here. I see quite a few questions in the Q&A, so if you are interested and want to stay around for that period, please feel free to do so. If you're dropping off at this point, though, thank you very much for joining, and hope to see you at the next one.